All right, so this is lecture 12. In the last lecture, we talked about frames, and today we're going to talk about kinematics, and they can kind of go hand in hand. We're going to need to use information from the last time to be able to do kinematics. And so we're going to start out with a review, and then we're going to add some new material, and I'm going to show you some Python examples of robot manipulators and doing the forward and inverse kinematics today. Right, so we're going to review coordinate frames. Everything in a robotic application is going to have some kind of frame assignment, and usually in the manufacturing too as well. If you go to any CNC machine there's a home position, and there's some kind of coordinate system for that particular scene. If it's a 2D, the XY grid. If it's 3D printer, you have XYZ, and you need to know where that home is. And you also need to know where your current tool is in the process, or where it's extruding material, or where the end mill is, depending on the manufacturing process. There's a tool frame, and there's a base frame, and there's coordinate frames for anything in the object there. And we talked about pose graph is going from one pose, which is position orientation, to another pose, and it's going to just be a series of transformations, which is going to be a dot product in linear algebra of a 4x4 matrix. And so if I want to go to from my base frame to the tool frame, through the robot, I could go to the robot, and then I could go to the thing, and I could do the dot product. And you still have a 4x4 matrix, and that 4x4 is going to have the rotation component is a 3x3 matrix, and it's going to have the translation component mixed together into a 4x4 matrix there. Frame assignment here is a industrial robotic system. It has a base coordinate frame and X, Y, and Z. And this is, I meant to update this. We usually have X's would be your RGB, so X would be your red axis. The green would be your Y, and usually the Z is your the blue axis there. And we have coordinate frame with the end effector. And we have objects here, and we have, in this case, we have a camera system here. Today, we want to program or tell the robot to the end effector position to go to an object. Say if I want to grasp this object here, we discover where this object is located using the camera, but now we need to be able to move the robot to go there. So we need to set the end effector position of pose equal to the object. And then we need to compute the joint variables here. If it's 6 degree freedom robots, 6 joint variables to actually make the robot move. And then it will get to that end effector will be equal to the object position, and that for you grasping. And then you just have to close the gripper, and then you can be able to do that. So we're going to talk about that motion, which would be the kinematics today. And that's really the goal of today's lecture. So just to review, everything has frames. And we could tie these frames together. Known information is going to be used a solid line, and unknown information is going to be used a dotted line. And we compute different path and trajectory to that. And it can be multiple solutions to get into that solution. And so, for example, if I want to go from the base frame to the gripper to see this object here, it will be able to, if the camera sees this object, it is going to have the transformation from the base to here, to here, to here, would be the same thing as from here to here. But you also use the camera here to detect that. And so there's multiple paths of finding that missing information. And so we also have redundancy in your sensors when developing that transformation there. So the transformation is just a position offset. We're going to use 3D space. So it's an XYZ offset is a vector. And then there's some kind of rotation, 3D rotation. So a rotation about Z, or rotation about X, or rotation about Y. And adding the position and orientation together makes a homogeneous transformation matrix here. And so here is an example. Here's my world frame, or sometimes they call it origin, and sometimes it's called a home position. And here is my camera located. And this system has 2 arms, a left arm and a right arm, and H is my object. And so if I want to know where the object is located in XYZ in its orientation, roll, pitch, and yaw, reference to the home. So we do this is the world is where we stop. And then this is the thing for transformation to home. So this the position, and this is going this direction because we're going from the world to the home. So the arrow is pointing that direction here. So if I want to compute that path, I could go from the robot to the camera to the right arm, and the right arm to there as well. I could also go from the world to the camera to the left, and then the inverse of that. And so you can see it's multiple ways, but they're all going to give you the same information, the transformation from the world to home, and be able to do that dot product. And that's going to give you the solution to where that actual object is in 3D space. And here are some properties of transformation. So you could inverse these by taking the negative, it just become the y. If you want to x over y is the same thing as the inverse transformation, but it's like taking it to the -1 power, and that will give you y to the x. Going from x to y to yz, you cannot change the order, or it's gonna, so that is not equal to each other. And here's some other different properties. Of course, the pose minus itself is going to be equal to 0, and some other things as well. And this is going to become a dot product in linear algebra. So we're doing 4x4 matrix multiplied by 4x4, and that's going to be equal to a 4x4 matrix. And so the 3x3 is the orientation. Sometimes is called the N0A. We may talk about that a little bit later. And then here's your position here. It needs to be a 4x4, so I could do the inverse. If I want to do inverse kinematics there, I need to be able to take the inverse of a 4x4. So it needs to be a square matrix to do an inverse operation. And this slide is just kind of representing the same thing here. Any questions so far? All right. So sometimes we want to take the inverse of that, and firstly for inverse kinematics, we could take the inverse. Since this is a special 4x4 homogeneous matrix, there's a shortcut. You could take the rotation part, you could transpose, which transposes mean the columns becomes rows and rows become columns. And you could also, the position vector would be the negative R transpose dot product. So you have a 3x3 dot product with a 3x1, and that will give you a 3x1 coming out of there. And that's a shortcut to doing a transformation as well. And then also you can use your basic calculators, whatever, to do this transformation as well. And I showed you a little bit of what a teaching pendant may look like. We'll have labs associated with it, so you guys should be able to get your hands and do this here. We're looking for the position of the tool, which is this guy here, versus the base of the robot here. And that's going to be the XYZ and the roll pitch and yaw here. So we computed in the last class where we wanted to go. And today we want to talk about these is equal to, this is a 6 degree of freedom robot. So this is joint 1, joint 2, joint 3, or we'll call it sometimes Qs for variables. And so we're going from the tool frame to the joint frame, and that's going to be the kinematics of a robot. So if I want to get to this position, I had to control the robot, the base, to 184 degrees, and so on here. And we can go back and forth between the joint frame to the tool frame by doing a forward inverse kinematics. So let's talk about some different types of robot configuration. We're only going to focus on one, but I do want to mention some other things you may not see here. So we do have closed loop systems. For example, this is a robot system here, and you can see that the base and the end effector are both grounded in the system. And so an example of that would be this here. If everybody know what this guy is. Have you seen these before? Yeah, it's Stewart platform. And so it could do a roll, pitch, and yaw really well. So a lot of flight simulators or something that we could kind of sit on top of that. But it's an example of a closed loop form situation, and it's still the same math here. And manipulators, and they do have some manufacturing. I'm gonna show some video later. Use a closed loop. Mill or something attached to that, and you can move the drill bit around that way. But robot manipulators are going to be mostly the open loop, meaning that the base is grounded and the end effector is not, and that C is representing the end effector, and I'm gonna move around. So just like a regular arm, or you can use these kinematics in for walking prosthetics as well as the same thing as your legs. And this will be your joints here, and this will be your foot there. And I want to know where that arm is or your foot is versus your body, and that was what we're going to talk about. So it's going to be an open loop mechanism here, and we're going to ignore this here, but the same theory is going to apply to these other systems. So in robotics, we have two main types of joints. There are some other ones down, but we're going to have a revolute joint, which means you have the ability to do this motion here. And then we have a prismatic joint, means you're able to slide back and forth. So for example, a CNC machine, traditional, it can slide an X in the Y direction and the Z. So that's a prismatic joint. And a revolute joint might be a robotic arm base there. And you can have a R and a P. And they do have ball joints, but it's mostly R and P. And to get a ball, you just do multiple R's at the same location to do that. So these are the most common configurations for robot. So here, Cartesian is PPP, so that's XYZ machine. You can think about that as a regular CNC machine. You have the RP, so that's going to be a rotation, and it's usually in the order. So the first joint is rotation, and you always start at the base, and you work your way to the end effector. So this is here is the first joint, and this is the second end joint. So the first joint here is rotation. Prismatic means this thing could go up and down, and this could slide back and forth. So this is a rotation prismatic. This here is a rotation joint here. So these are all, each one of these mean degree of freedom. So this is 3 degree of freedom. This is 3 degree of freedom. All of these here is a 3 degree of freedom. This one rotates here, it rotates here, and this guy goes up and down. This is where we mostly work at, the RRR, articulate robots. It rotates here, it rotates here, it rotates here. And the SCAR is a rotation, and prismatic here. And so I'm gonna give you a little bit of history here. So the first arm was developed at Stanford in the 1969, and I'm just gonna play, we're gonna Let's show you a little bit of what it looked like.
Absolute Cartesian formation. You could pass that to the manipulator, which is also calibrated in that three-dimensional space. And then you can move its hand to any point in that space with any orientation. And this was all based on an absolute Cartesian coordinate system. Here's the work table holding the manipulator and the camera.
So this is the late 60s is when the was driving the force for robot manipulators. And this is where the industrial revolution and things here was happening in the United States here. But Stanford was leading the way. They even have camera systems for the seeing the different objects there.
Divided with a turret. This was a film.
This is the first commercially available, was the Puma series, and we still have 2 of these in the EB2. And here, used to use this as a lab. We used to do a drawing exercise, so the robot had to draw a particular object here. These are direct gear drives, so these have a lot of torque. These were used in the automotive industry. Detroit still have a bunch of these that were kind of donating around for welding process and just doing normally assembly there. So these are traditional industrial robotic systems. Here is, so Tom is moving a little bit forward, and now we have one of these in the actual Fitzwiller, the automation lab. If you see that little thing in the corner is on the floor, the SCAR robot, and it's good for pick and place operations. So we have a rotation, and prismatic link there. So next time you're in 2311, let's look in the back where the window is broken on the floor. You'll be able to see this guy here. But see how fast it is for motion. So this is one of the faster robotic systems here. it's still 3 degrees of freedom. So you lose, so you cannot do X, Y, Z, row, pitch, and yaw. So you have to choose your degree of freedom. So if you want to get higher degree of freedom, you have to have more joints. And so we started to investigate it, better system. Here's a gantry, which is you probably all used before in some fashion. Some kind of SY, either a laser cutter or a PCB thing, or any kind of major, just like low end manufacturing. It's just X and Y, and it has a small TSs. These are good for position control, but not orientation. So I cannot do any kind of twist motion with these guys here. And this is parallel, so this would be a closed form robot. They're getting a little bit more popular, but they're still not as popular as open loop.
Come down the line here.
But you can do a lot of good stuff with that. They just never really caught on that much, but they are still, ABB still are leading the way in this here. They're just not as popular, but they work really well. And this is moving to more we have here is the it's still industrial robot, but they're more called cobarts, which are more friendly there. And this is what we're going to be using. One of the systems we're going to be using in the labs to just kind of play around and do taking place there. So we're moving to a 6 degree of freedom system. So we could do a lot of different motion that we couldn't do with the 3 degree of freedom systems there. This one, just the FOB stands for the amount of payload it can have. So I think it's a 5-pound payload is the max. And they have a UR5, they have a UR10, and they have UR3 series as well. And so we're going to spend a little bit more time with that in this class here. So now we're going to introduce 2 other terms, and there's going to be the kinematics. It's going to be the 4 kinematics here. So where is the robot end effector is, if you know all the joints. So if I have a 6 degree freedom, given the joint angles, my robot end effector, which is usually what I call the gripper or wherever what is actually making contact with the object, what is his XY position? What is his roll, pitch, yaw position? And then the inverse kinematics is the opposite. Given its X, Y, Z position or row, pitch, and yaw, given that 4x4 matrix, what are the joint variables to get to that location? And today I'm going to show you how to do the math to come up with the forward and the inverse kinematics of any n degree freedom system. And then we can do some examples in the lab with the ABB and the FANUC and the UR system there. And so here is it in the diagram here. So joint variables is called Q's. So this would be, in this case here, it rotates here. So this is a rotation here, it rotates here, and then there's 3 rotations at the gripper wrist. So this is a 6 degree freedom robot. So there's 6 Q variables. And then I have position and orientation there. And that would be the direct kinematics. And then if I want to go backwards, inverse kinematics, it would be the opposite here. And so, for example, 3 degree freedom robots, meaning 3 joint variables, Q1, Q2, and Q3. I get this transformation matrix doing a 4 kinematics, and it's still going to be a 4x4 matrix. So what is this representing? The 3x3 represent here? The rotation component, and then there's the position component here. And I'm going to explain to you this, but this is going to be a series of 3 transformations for each degree of freedom. So for 3, we have a 3 degree of freedom robot, so 3 joint variables, and you still get a 4x4 matrix out with the position and orientation. And to compute that 4x4 is going to be a series of 3 transformations, 0 to 1, based to the first degree of freedom, the first degree of freedom to the second degree of freedom, and the second degree of freedom to the third freedom. And most robotic systems are using a 6 degree of freedom, and it actually makes the math a little bit easier. And it's still going to be a 4x4 matrix. So it doesn't matter how many degree of freedoms you have, it's going to become a 4x4 matrix because each one of these is a 4x4. 4x4 times a 4x4 is going to be a 4x4. It still has its position and orientation here. So 6-degree of freedom robot, 4x4 matrix with the rotation and location, and the 3-degree of freedom, the same thing out here. And we're going to compute this map today and show you how to come up with the 4 kinematic astral matrix to represent that. But it's going to be a chain of transformations from the base all the way to the end effector. It's how you compute this 4x4 matrix. So here is an example here. This is going to be a 1-link arm. And I have, here is the base here. And I want to know the position of this end effector. How can you compute this? Where the E is located? So you have X and Y, and this is 0, 0. And I have 1 link here, and this is a theta here. I would like to know the X and Y of that graphic. How can you compute that? Given the length here, is to say this is A1, and let's pick it 1 unit.
So A1 time.
So you can just do here, and then remember your socket tore. This is sine opposite of hypotenuse. And I need to compute, this is my theta here. So sine of theta is equal to opposite, which would be my y component over a. So I can just say this, and let's just move it over here. And then x is going to be equal to a cosine of theta. And so now I can compute my an xy position based on the theta there. All right. And how many degree of freedom is this system? 1. Yep, I have 1 input. So my theta, which I'm going to call Q1, controls my system. So I can I cannot, this is a fixed length. So if it was variable, then that would be 2 degree of freedom. So given my Q1 value, I could get to some XY position there. So what is the problem? What if I want to pick up this location here? Is that possible? Yeah. Because it could only, this is going to be a circle. Yeah. So to get here, I'm going to have to add another degree of freedom. And so now, or let's go here. There's no way to pick that up here. And so now I had to, let's just do here to match my notes here. I had to add a separate link to get there. And so now what it is, I'm interested in X. Let's call this X1, X2, X. So what it is, it's XY position. And this is X1 and Y. So I'm looking for X2 and Y2. How can I compute where this is versus the origin?
Do you know the length of that?
Yeah. Let's say this is A2, and let's say it's equal to 1. A2 is equal to A1. And so this would be a real robot, so you manufacturing, so you know the geometry of your robot system.
Do we know the joints?
What was that?
Do we know the second joint?
The arrow,
Angle?
I mean, the angle.
Yep, we need to know this. So this is going to be called another, this would be Q2. So now we'll have 2 degree of freedoms. And this, we would say, we'll call it, we just need 2. So there's going to be theta 1 and theta 2.
That's the angle with the horizontal.
Yeah, so it would be, so this theta would be, yeah, it would be horizontal here, it would be the angle between this here and this here. So the total angle of that is theta 1 plus theta 2. So if I'm looking for, so this is x1 distance, x2 is this distance here, is equal to what?
cosine of
It's still gonna be this A2 here, and it's gonna be cosine of
2 pi.
this
Theta.
theta, yeah, Q2. And then the Y2 is gonna be equal to A2 sine of Q1 there.
Don't you have to do plus x1 and plus 1?
What was that?
Don't you have to do plus x1?
Yep, so we have, that's just the small part here. So that is not, we want to do the total, so this is gonna be, we need to add in this x1 plus this dot here. And so we're gonna add in the total x2 is gonna be x1, which is this A cosine of Q1 plus that, and the y2 is gonna be the A1 sine of that Q1 plus the T here. So you can compute in a matrix format. This is going to become cosine of Q1, cosine of Q2, sine of Q1, sine of Q2. Oh, sorry, I think this is supposed to be cosine. You could convert this into a matrix format there. And so we could use geometry to figure out where, I think this may not be 100% right there, but it could be, we can use geometry to figure out where the end effector is and figure out the joint angle. So that's going to be kinematics. Given the Q values, where's my XY location in space there? So here is probably the better solution here. So here I got two links here, 2 degree of freedom, and using geometry here, I did some math. It becomes sine of 2 here, and I'm left with yeah, made a little bit of error on the board here, but this is the XY position for a 2 link here. And so we can add more and more links, and you could add more, and you can still do the math there. And so this is good, but you can see as the degree of freedom gets higher, it gets a little bit more and more complex to do the math there, but it's still possible. And so I don't use this method, but it's still a geometric approach to solving the problem. Let's revisit what we talked about yesterday, Tuesday. This is a better method to doing it here. So remember in the last class, I'm just going to say we had a roll frame, and I had the camera frame, and I wanted to get to the object here. And I was asking you, so what is this is the transformation from the roll to the camera. This is the transformation from the camera to H. What is the transformation from the roll to this?
transformation of word to C and then C to H.
Yeah. Is that what you said?
Yes.
So it's just the dot product or the matrix of the dot product of 2 4x4 matrix there. So let's keep that in mind. So let's go back to the 1 link example. This is my frame. Let's get another color here. So I have a frame at the base. And then I have one at the end effector here. So I do the same kinematic chain here. Let's do, this is the base, and this is the end effector. So I want to go from here to here. So what did I do to go from this one to here? The red to the Right. So I'm originally, this is my origin. And then I went to here. So this is my first degree of freedom. So what did I do? What's the difference between this one and this one?
Rotation.
Rotation. So I did a rotation about, this is my XY, so that has to be a Z. So that is my first version, and that allows me from here. And now if I want to go from here to here, how did I do that? From this guy to this guy.
Transformation.
I did a transformation, and I know the length of the robot. So then I do a translation of A1. And that is gonna be the base to my end effector. So I'm doing a kinematic chain. If you want to think, so I did a rotation along it, and then I did a translation to move it. So this is going to be equal to still going to be a 4x4 matrix, correct? Is everyone get that there? So let's add the other link there. So now, where is my? So this is the first example. What is my base to E2 now? Still here. I got to work from my base all the way up to my end effector. So I rotate it. Then I translate it right here. So this is a rotation. Comes to translation. Now I'm here. And now I need to rotate it again, the line here. So there's another rotation. And this is a rotation Q2, this is a rotation Q1, and then another translation A2, if this is the length of this is A2 and this is A1. And what do you get out of that that transform that if you do the dot product here? You still get a 4x4 matrix. You always gonna get a 4x4 matrix out. And we know the rotation matrix, we know the translation matrix, and we just do the thing. So I could do any kind of configuration I want to. I could have the robot coming out of the page, whatever, and I just did a transformation through each one of those, and I computed that. And that's going to give me a 4x4 matrix, which is going to give me the 4 kinematics of the system. And so I'm going to do show some pictures on the board here. So here is that SCAR robot. And what you would think, if I want to go from the base to the end effector, how can I compute that? What's the kinematic chain to do that? So I wish I could draw on here. So I'm at the base. I probably can actually. Let's see here. So I'm here. This thing can rotate. So I have a rotation here, the line up here. Then I could translate down. This is A1. I'm going to go to here. And then I need to rotate here a little bit. And then I could translate to here. And then I could translate here. So I could describe any robot system by a series of just rotations and translations, and depending on the axis of the system here. So for example, this is what it will look like if you do the chain here. So I did a rotation about Z here, then I moved the unit X, and then I did a rotation about Z, I move the unit S, and then I do the last transformation here. And that's gonna give you a 4x4 matrix there of the system. And then this is a matter of just crunching numbers to actually get a real system to do that. And here's the Puma. So it's still a rotation. You just need to know the geometry of the robot. Usually the manufacturer is going to provide the lengths here. Length 0 is a certain height and so the mass. And this is how the kinematics are usually provided by the manufacturer, but you could measure if you and compute the kinematics of any system and do that and come up with the math on your own. So if you're designing your own system, or you're going to take a system out of the lab and you want to be able to program the kinematics, you just need to go back and then measure the length of these joints, figure out how they rotate, and then do the dot product there, and you'll get a 4x4 matrix out. It gets longer and longer as if you do them symbolic. But if you actually have numbers in there, it's still gonna be a 4x4 there, and then you'll be able to do the kinematics. I'm gonna show you some Python examples. So you don't have to do the 4x4 by the 4x4 and all that by hand. But my old professor actually made you do all that by hand. The rows and columns and stuff. I don't remember how that actually even works anymore. But it's just a 4x4. It's a linear algebra problem there. We're not going to test your linear algebra skills in this course, and so I'm just going to show you Python to do that. And so this is one of the systems here, 6-degree freedom robot. We have 2 of those, and it's going to just be the same thing. It's going to be 6R. So the rotation. Let's see if I could draw. Rotation here, and then you can compute the length here. You say that's A1. It's going to be another rotation. Actually, it's rotating here. So you just figure out what that is, and then you got a transformation here, and then you got a rotation about here, and you so on. If you knew the measurements, rotation here, and you can just keep going till you get this R in the system, and those links are provided by the manufacturing of the system, so you can build a kinematic model of this Fennec system. They do provide this information, but if you didn't know that, you could actually come up with your own matrix for that here. All right, so this is a better graph of what I did before here. This is just a rotation of a single thing here. You can see it's the rotation component, and then I added a translation component. And we already talked about post graph, so that's going to be equivalent from the base to the end effector. Here is a 2R system, 2-degree of freedoms. It rotates here and rotates here. I rotate it to get this aligned, and then I translate it. And then I rotate it to get this aligned in a translation. So a rotation, translation, rotation, translation is a 4. This guy here is a rotation, and this is prismatic, means this slides up and down. So the length of this varies. I see a rotation, and then this other joint is a translation component because this is the length is variable. And robotic system is just usually a combination of a mix and match between these different configurations to do that. And so in the last class, I showed you these libraries here, and I'm going to use these here to help me do the math a little bit easier. So I could just plug in these numbers, and I would have this numerical answer here, and I don't want to do that using my calculator, so I'm going to use Python to do that. And I'm mainly going to be using this Python library in the spatial math, which lets you do the dot products and things, vectors, rotation matrix from there. And I'm going to show you some kinematics and stuff using the robotic toolbox here. Again, this is where, if you want more information on this is where I'm getting this stuff from. To install it, you could just do this pip3 installed robot toolbox, and you will be up to and ready there. All right, so the first thing on the show is the robot. Let me make sure. Yeah, robot example 2D. Let's do that one first. Let me just close some of these. All right. So I imported my robot toolbox. I'm going to use DT. I'm going to use math here for the pi div here. But here is my example here. I have a single linked. I did a rotation. And then I'm gonna do a translation, and my length here, I just call it 1 unit. Here, I do a dot product here and did transformation. We're gonna use this number, whatever you call this thing, multiplication thing to do that, symbol for the dot product. And then I want to find a solution with the variable. So I want to know what it is at 30 degrees. I think pi over 6 is 30 degrees there. And so this takes radians. I could use the math dot radians and convert from degrees here. And then I'm just going to print the position of the rotate. I'm just going to show you some other things here. I'm going to leave this off for right now. And I'm just going to run this code here. I think Zoom is slowing down my processor. Shouldn't take that long to. Okay. And you can see it's the rotation Z, and I'm going forward, so it's a plus. And this is my 4x4 matrix. So the red is what is equal to what again? The rotation, and then this blue is going to be, and so the robot's going to be at 30 degrees. Where is my robot end effector located at? What was that?
Almost 45.
No, what position?
Oh,
SYZ position.
0.866.
And then since it's a 3x3 example, is the 0, 0 in the Z direction. Its orientation, since we know the orientation because we took 30 degrees in there, so this should be equal to 30 degrees here. And so I just took this 3x3 matrix here, and I convert it to row, pitch, and yaw. And there's a 0 degrees in the X direction, 0 degrees in the Y direction, and 0 degrees and 30 degrees in the Z direction. So it's a rotation vector here. There's also this teach thing, which is a pretty handy thing to use. And let's see if it runs a little bit faster. And I can move the robot around, and I could see my interface. Of course, it's only going to be a circle because I cannot get to any other position. So so given 74 degrees, my robot is located at this XYZ location. And so a 1 degree of freedom robot is not very useful. It's just going to draw circles. So let's just move to a higher degree of freedom system, which is going to be this one here. So here I added that second jump that we had earlier. And so now I have 2 degree of freedom, a Q1 and a Q2. We already did the math earlier. And we told that was a rotation, translation, rotation, translation. They both going to be 1 unit in length here. I'm using A1 twice here. And I said this is at 30 degrees here. And this is here is 30 degrees here. Where is my XY Z position of the system? And it would just be the rotation times the translation on the rotation translation, a 4x4 matrix. And I'm just going to use Python to compute that for me. And this is the code here for that. I'm just going to run this guy. And located at 1.866 units and Y position 0.5 units for that particular robot system. And this is looking more like if you want to model a human leg, you could just keep adding. This would be your I forget what muscle that is here, and then this would be the joint down here. So you could do human kinematics as well and figure out walking, gait motions, and things like that based on. And so done a study years ago, putting accelerometers on the body and then kind of modeling and simulating a person walking and looking at their kinematics before. But so this is a 2-degree of freedom robot, very similar to a human leg or an insect or something like that. You could to model there, but it's still, this is only going. I cannot do anything in the Z direction here. I have better the more degree of freedom, the better XYZ, or the more places you can actually reach in time. But I still can't roll and pitching y'all. Will have to add another degree of freedom, and so I'm just going from a 2-degree of freedom to an n number degree of freedom, and you can have redundancy degrees, so you can have a 60 degree of freedom, but then you're going to be kind of hard to build the machine. It's going to also drive up costs. So usually 6 is the good number because you hit all the degree of freedoms. So that is going to be. Let's just move up to a higher order, and so let's go to a 3-dimensional drawing here. And so now I am doing rotations in Z's, but I'm also doing rotations in Y. So I want to get out of the board now. And so I'm just adding. So this would be more like that Scar robot. So I figure out the right transformation for that particular robot here. So something like this. Once you have that, you could just put it in here and you could kind of confirm to make sure that it matches by just kind of simulating and then go back and forward. So I did the same thing. I created a transformation called E here. All of these have 1 unit length. You can play with different lengths here. I'm going to get the structure here. So I'm adding a new command here. I want to get the n degree of freedoms so I can know what the robot is. I'm going to start and compute the position with all zeros. So that usually zeros is your home positions. And I'm going to move from there, and I'm going to extract some different information from here. So let's just run this guy as well. And this is my 3D, I believe. And let me just move it around so you could kind of see a little bit better. If you probably shouldn't have started at 0, 0. It's kind of hard to see things. But you have a row pitch and y'all at the end effector. And here we go. It looks better this way. Just slotted her around the corner and go up or something. So this is looking more like the URs or something like that. So you can be as creative as you want to. And given these joint angles, this is going to be my XYZ position here. So is that the forward or inverse kinematic? Given these joint angles, here's my output. Is that forward or backwards? Yeah, that's what we consider the forward kinematics. Given this X, Y, Z, computing the joint angles would be my inverse kinematics. And so that leads to the next thing here. Let's just go back to my presentation. Let me just rewind back just a little bit. So we started back with this picture here. I want to pick up this toy animal with my robot gripper. So I use the camera to figure out where this thing is located in the space. And now doing the chain from and I know where the camera is located now because I have my forward kinematics in my system. So I know where the camera is located with the base. And now I know where the camera versus the object. Now I know where the object is located with the base of the robot. So now I want to pick up this gripper, this object with the gripper. How do I pick it up? What was that? Yep. So I know the location. If I set my gripper equal to the location, then my gripper will be at that location, and then I could do inverse kinematics to figure out the angles I need to actually get to move the robot to move to that position. And so this is what the inverse kinematics is going to do. And then you would just program the robot joint one, do this and do that. And you could do a closed loop control system to actually make sure the joint is actually equal to that joint.
You know,
So the inverse kinematics is going from its position, orientation, pose, 4x4 matrix, and I'm going to compute the joint. And for the in degree of freedom system here, most likely we're going to try to stick with 6. It's going to make the math a little bit easier when you try to inverse, because remember, we could take the transpose of the inverse for a numerical solution. And sometimes you cannot be able to compute the inverse kinematics. So it may actually give you multiple positions here. For example, I want to pick up this object here, given this robot system here. I tell it to compute the inverse kinematics. What would happen here? So this has a T matrix, 4x4. And I'm going to set my end effector, which we can call E, to my object H. In this case, it's not physically possible for that to do that. So it won't converge on a solution, or it may give you a solution that's invalid. So you need to also check. Once you find this is Q1, you're gonna give a Q1 and a Q2 to give you that position. And once you computed that, you need to verify that you can actually reach that position there. You also have situations of, for example, you can have multiple solutions. So if I want to pick up an object here, I have a Q1 and Q2 here, but I could also have, so like an elbow up and elbow down. I'm still at the same position to get, and so I have 2 different Q1 and Q2 out to give me things here. But the pose might be slightly different. So you could also need to check and make sure there's a valid solution there. And make sure your solution is not having, also you want to do eventually collision avoidance. You want to make sure your wall is not trying to go through a wall to pick up an object or something like that as well. So we're going to use the inverse kinematics to kind of go from the position orientation back to the joint angles here. And there's several different methods, but the method I'm going to introduce for this class here is more of an optimization. Since we were IOC here, we're going to use the forward kinematics to compute the inverse kinematics. So we're going to guess what Q1 and Q2 is, solve for the forward kinematics, and we want to optimize. We want to make sure when the end effector equals the goal, so when that, and then that would be your solution. So we're just going to vary Q1 and Q2, look at the answer, and keep varying it to the end effector is actually equal to the target, and we can do an optimization problem. And when that is equal to each other or close enough to a certain conversion factor, then that is your goal there. You can also, since it's a 4x4 matrix, you can just take the inverse of it, and you can also get a solution for certain end degree of freedom robots there. It doesn't necessarily always work when you try to do an inverse of that matrix there. And so it may not be possible to get a solution, or we're going to have an approximate solution by doing this particular method here. And I want to show you what that looks like in Python. So I have a 2D example here, a vert here. So here is my my description of the robot. So this is 2 degree freedom system. It's looking like this here: a rotation, translation, rotation, translation. I want to get to this desired position at 0.6 and 0.7. I need to compute the Q1 and Q2 to get me to that location. It's what the answer is looking for. What Q1, what Q2 value gets me to that location here. So that's my desired n is XYZ. So I added a 0 there. I'm using this lambda function, which is like a I'm gonna use the NumPy library. I'm going to put in the forward kinematics. I'm only care about the position. I could care about the position and orientation at that point, but I'm going to take the current position minus my desired position, and when that's equal to 0, then I'm at my goal. So I'm trying to look at the error of the system, and I'm trying to minimize the error of the system. And when the error is equal to 0, closer to 0, it's right here. I'm using the optimization function. Then I am at my goal point. And then here, I'm just going to print out the solution of optimization. It may not converge on the solution, so I'm going to print it out, show you what's there. And then if it does converge, I'm going to take the position component from that solution, and I'm converting it to degrees because the answer to the solution is in radians. And I'm going to leave. And then I want to check my solution. So I'm going to put my solution back in just to verify I'm at my goal. And so I'm going to run this without teach first here. And this is, so I'm looking for 6 and 7 here. And it is a 6 degree of freedom, our robot, so 6R system here. And this is the forward kinematics at the 0, 0 position. So there really doesn't mean anything here. I don't even need to print that. And I going to do this minimization function. It did not converge at that position I needed to, but it gives me an X position and a Y position, and this Y, X and Y. This is the first joint variable, and the second is in radians, and I convert it to degrees. So it's saying that it's possible and around negative 13.5 degrees for this joint. And the second joint around 125 degrees here. I should be around that certain position that I'm my desired position here. And I'm going to do a teach here just to kind of show you what that looks like. So at that position, negative 13.2 and the 128 degrees, I'm actually at 0.6 and 0.7. So it is actually pretty close. Doing some rounding, that in this case is actually the right numbers. There's probably some decimal place numbers behind there too. So that's how, so now that I have this information, now I just need to program a robot to go move from wherever you are to negative 13.2 degrees and move the second joint 1 to 125. And most of the time we move both joints at the same time. We don't do joint for one and then do joint. We just move both incremental, and then we get to the final destination. So that's going to make the 2 degree free robot move to the XY, the desired location and system. So now we could go, that would actually go pick up the road, and then we just close the gripper. So now we're at the location and we just grabs it, and then we can move to another location here. And so here's some code for later for that. So we're going to have one more homework assignment that goes through this lecture and the last lecture. So you can actually type these things out. I'm going to give you a robot configuration, and you can do the forward and inverse kinematics. But in the lab, we're going to do, it's really easy with the robots because they do this for you in most cases. When you move the robot using this pendant, it's going to automatically compute, and that's what it's doing in the background, is computing its forward and inverse kinematics, and you will see it on the pendant itself. And so most robot systems you can just look at, but the actual mathematics behind it is what we're doing. Is that linear algebra that I'm showing you before. So if you were to custom build your own robot system and want to know, you can measure, you 3D printing or making these, so you know the links of this here. You could, if you wanted to figure out where the position it is, you could just do this. You could figure out the kinematic chain of that and do the dot product there, and you have your forward and inverse kinematic to your custom machine or custom automation equipment, and you could go to different positions by just telling that servo motor or whatever to rotate to that position or whatever. And so that's kind of where we're going with that. It's for this course. So look forward to a homework assignment on that for the next class. And then we're going to, now when in the next class, we're also going to talk about, okay, we have this here, let's program these robots to actually move. And so I'm going to show you different programming languages for industrial robot systems, and I'll show you the ones for the which will be the FANUC system. They all use a common language, Corel for the larger systems, and then each one of the other systems have their own kind of software, and we'll show you that. And then we'll have 2 labs where you program. We'll use 3 different machines, so there'll be 3 groups, and you rotate to each one. So you have the chance to program all 3 of the machines there, and that'll be the last lab. So a lecture on the 31st on programming, and I'm going to sign the homework 3. Then that will be the last official lecture. And then November 2nd and 7th, we will do the labs. We probably have to rotate that, and then November 7th will be the homework is going to be due. And also project description. So now it's trying to think about, we talked about the IoT, we talked about robots, we talked about PLCs. It's time to think about coming up with a class project. You give, if you have an idea, you can write down a description, and that's going to be due on the 3rd. It's a paragraph of what your team is, your teammates, and what the description. And I have some ideas if you cannot come up with some, but you can kind of create your own project there. And then on the 21st, we will have an exam, which is be all the homework 1, 2, and 3, and some based on, and then the lecture notes will be based on that too as well. And that is it for today. I will stick around for any questions and answering things.